We have Tess BOIVIN, who is an ML engineer working for NXP. She graduated in 2020 from the University of Sophia Antipolis in the south of France, a beautiful, beautiful place, where she is working on deep learning-based speech enhancement and complexity reduction for audio front ends. Thank you.
Thank you. So I have to say also this work is a collaboration with my team Aurélie Donjon and Guido Roncarolo from the Voice and Audio team in Sophia Antipolis, France. So first of all, a few words about, okay. So the main idea behind the Voice UI is that you can wake up your device and control it, or control action using your voice. So it's built like this. We expect the speaker to be at a 3-meter distance, and we will receive the speech using a 2 to 3 microphone array. The speech is sampled at 16 kilohertz and in 16 bits. Then we have the low power VID, which is here to minimize CPU load when there is no activity. Then you have the audio front end, which is here to enhance the speech. And then you have the wake word engine and voice command engine. So basically, you can choose any keyword you want, like for example, hey NXP, and any set of voice command you want, like next, play, or volume up. So such a device is constrained by low power because our current solution runs on NXP-RT1060 that runs at 600 megahertz, and we also have a huge constraint on low latency. We have a trigger delay to be inferior or equal to 200 milliseconds to fit market requirements. And we have also a high performance requirement with a false positive that needs to be inferior or equal to 3 per 24 hours. So just for you to know. Sorry, this is not my slides. Okay, there is. So this is the RT1060 block. And it runs with the Arm Cortex-M7 at 600 megahertz. Okay, so as I was saying, you expect to have false positive rate to be inferior or equal to 3 per 24 hours. And just to give you an overview of what it corresponds to, so having a frame that is 10 milliseconds, you will have a false positive rate of 34 to 10 - 6%. Which corresponds to a true negative rate of 99.99996%, and you all know how it's difficult to achieve almost 100%. In this talk, we will focus on the audio front-end part. So why do we need an audio front-end? It's because real life is noisy. So taking the example of the device within the living room, so you want to control your device, but maybe your TV can be turned on, or maybe music can be played in the background, or even more, someone can be speaking at the same time you are. So this results in obtaining a noisy speech as a combination of speech and noise. And what we have seen is that we have a huge drop of performances. So here we observe the wake word hit rate. So hit rate is the percentage of well-detected wake word. So it is music condition from very noisy condition to less noisy condition. And we can see that in very noisy condition, we have a huge drop of performances. So the idea behind the audio front-end is to enhance the speech, remove the background noise in order to get back the clean speech estimates. And to do so, we choose the multi-linear channel filter. So I will introduce you to what it is. So first of all, the parameters. So a time frame is expected to be 10 milliseconds, sample at 16 kilohertz, and FFT size is 512 points. And for the rest of the presentation, I assume that T is for frame indexed and F for frequency bin. So you receive the multi-channel audio and compute FFT on it to have the time frequency signal. Then you extract the reference channel and give that to your NN mask estimator in order to predict a speech mask. So what is a speech mask? Is a 2D array from frequency and time, and each pixel of it corresponds to the probability of the time frequency element to belong to the target speaker. So considering your input signal being a combination of speech and noise, you can compute the ideal ratio mask. So I put here the formula. And so this is the target we were training our neural network with. Then once you have your speech mask, you can apply it to your FFT and calculate the spatial covariance matrix in order to solve the multi-linear filter and get back your speech estimate. And once you have your speech estimate back, you can give it to your wake word engine and voice command engine. But in its classical form, it's not it's not designed for embedded systems. First of all, it's not robust to real-life dB level range. Second of all, the NN estimator was way too big to fit on platform. And third of all, like a multi-linear filter is not computed in real time. So we will see how we solve these issues, but it's also worth to mention the challenges of the solution. So the main algorithm are the wake word engine and voice command engine, and audio frontend is to this. So we have a huge size constraint. And also we focused on increasing performances of the wake word and voice engine, and we didn't see any clear correlation between classical metric like signal to noise ratio or signal to distortion ratio improvement. So first, our neural network was not robust to input dB level. So you expect your input dB level to be between -40 dB full scale and -60 dB full scale. And we have trained our neural network at -40 dB full scale. And we see a drop of performances at -60 dB. So this was the mask we obtained at -40 dB full scale. And as you can see, the mask at -60 is like really degraded. And this is compared to the Oracle mask, which is the target we estimate. So in order to solve that, we apply transformation on the input data. It's normalize the data based on energy and root compression to arrange the distribution. So this is what we used to have. So in distribution at -40 in blue, -60 in brown, and what we have after applying the transformation to distribution. And as you can see, it's like much more designed for neural networks training. And that's the mask we are now obtaining at -40, -60 versus the Oracle mask. So second of all, our NN was way too big to fit on platform. So our neural network was expecting 21 consecutive frames of 25750 FFT frequency bins. And the neural network was taken from a state-of-the-art neural network from Furno-Elnal at Loria University. And it's composed of 3 convolutional blocks followed by a GRU. And then you have the dense and the sigmoid activation. So this neural network was 470K parameters, but it was also 33 million max. But if we wanted this network to run, to keep like real-time prediction, CPU should run at 63,240 megahertz, while our objective is to be like less than 300 megahertz. So in order to solve that, we explore several things. So first of all, we say that, okay, maybe the CNN part can be reduced. So we also tried depth-wise separable convolution. So considering a layer with an output filter this way, we were computing 1.5 million operations. If you use depth-wise convolution, it's only 220K operation. It's like 10 times less. Then we also focus on reducing the GRU. So maybe the GRU features could be reduced, but it was still not fitting on platform. So then what we said that, okay, the CNN part is here to embed some feature, but what if we directly give an embedded features like the log, the mail spectrogram, and we only keep the recurrent layer? So actually, this is what we have been doing. So now our neural network is expecting 21 consecutive frames of 40 normalized mail bin, and the GRU has only 37 units, and 37 is because we have also optimized the network architecture using hyperparameter tuning with random search using RayTune tool. So the network is only 18K parameters, and it is 200K max, and it's running at 300 MHz in C floating point code. We furthermore improve this solution by performing 16-bit symmetric post-training quantization using GLOW. So from the 300 MHz in float, now at 150 MHz in quantized version. And we also use truncated backpropagation through time to take a frame-by-frame decision. So we used to have 21 frames to compute one output, and now we have one-by-one output. And this network is only consuming 28.2 MHz from float, and in the quantized version, it's only 12 MHz. So that's for the network part. And for the MWF part, we used to compute the spatial covariance matrices not in real time, but now we recursively update covariance matrices of noise to solve the multi-linear channel equation. So I put it just here. The chosen solution is only 18K parameter and n-quantized in 16 bits, taking only 12 MHz to predict a mask frame. And the full speech enhancement solution is taking 160 MHz in the 3-microphone configuration and about 105 MHz in the 2-mix configuration. So to measure the improvement we bring to the wake word detection and voice command detection, we derive an Amazon far-field test. So you expect a test file of being composed of 50 pairs of wake word and voice command. The speaker is supposed to be at 3-meter distance from the device. We test in different conditions, so in silence, but also using pink noise, music, and also in a multi-talker scenario. And the signal-to-noise ratio is taken between 0 dB, so same level of speech and noise, and 15 dB, so you expect the power of speech to be about 4.5 times the noise level. And we are measuring true positive wake words, so well-detected wake word at the right time. So this is the performances we have in silence. So we measure in silence because we don't want the audio front-end to degrade the performances when there is no noise. This is what we obtained in pink. So you can see that we have, you can see that we bring 10 dB improvement. So you have the performances of the input in blue, of the 2-mix solution in green, and 3-mix solution in orange. And you can see that we bring almost 10 dB improvement in pink. If you look at music, the 3-mix solution is bringing a 60% improvement. And if you look at the multi-talker scenario, then we bring some improvement, but in low SNR condition, it's still like really difficult to know who is the target speaker, and so who you need to enhance or who you don't want. In conclusion, we have been working on speech enhancement solutions for low-power devices. The solution is now real-time and embedded on a small platform, and we improve in average by 40% the wake word and voice command hit rate in the 3-mic configuration. So thank you for your attention, and if you have any question, I will be pleased to answer.
Thank you, Tess. One question that jumps immediately to mind is that you're spending 160 megahertz, of which the neural network is only 12 megahertz. Of the other 148 megahertz, what are the big consumers of compute in the platform?
Okay, so in order to solve the multi-linear channel filter, you need to sometimes invert matrices, and this takes like a lot of computation. It's like most of it, actually.
Yeah. You seem to get a lot of benefit from this dynamic beamformer. Can you say a little bit more about the beamformer as well in this system?
Yeah. So in fact, applying the mask to the FFT, you perform like a spectral denoising. And then when computing the spatial covariance matrices, you apply spatial beamforming. So that's why we have a huge gap between 2 and 3 microphone solution, because you benefit from having another microphone so that you can know a bit more about where the target speaker is within the room.
Okay. Other questions here? Can you say something more about how you did the normalization? This is actually a really important question in a lot of audio systems, particularly because there are potentially interactions between the gain control and the neural network downstream. You know, in particular, you'd really like it if the system could differentiate noise level variations versus speech level variations. Because a gain control may want to behave differently depending on whether the noise level is going up and down or the speech level is going up and down. How did you think about the levels as they affected the neural network? I'm
not sure I get like 100%.
Yeah, it's a little bit of a vague question. Can you talk a little bit, like, for example, about the adaptation rates in this gain control or normalization and what you had to optimize for in deciding what the adaptation rates were? Because obviously, as you normalize to a varying level, you have to decide how quickly the amplification will be increased or decreased. Was that an important part of the design of the system, and did that affect the neural network behavior at all?
Oh, so basically you receive some you receive some speech and noise between -40 and -60, but
yeah.
It can vary in time from -40, -60, right. And so by applying the normalization, it's inspired from per channel energy normalization. You will directly normalize the feature you receive in order to give your NN something which is robust to be at -40 or -60 dB full scale.
Thank you. Question?
Yeah, question. So obviously when you're doing these tests, they're obviously happening in a consistent environment. With this implementation, how adaptive is it to a brand new noise coming? What is the actual length in seconds before it actually starts to dynamically adapt to these noises?
Oh, I think it's about you adapt real time to this vibration. You have an initialization period of about 60 milliseconds, and then you adapt frame by frame. We have tested, for example, changing the noise source at the middle of the test, and it still adapts very well.
So because I've previously used other algorithms, it's not they're normally taking about 3 seconds for them to converge. So are you saying the conversion time is like hundreds of milliseconds, or adapted to going from pink to music, for example?
Yes, so I think it's about you expect to give 10 frames, so 100 milliseconds maximum.
Okay, all right, thank you.
Any other questions here? All right. Thank you very much, Tess.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are Arm, Deep Light, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymex, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.